What if I got bad grades on the stuff I just wanted to memorize?
Okay, we have our second exam a week from today. And it'll cover everything up through 2.7, which is related rates. I will say that the problem that I'm going to put on the exam in terms of 2.7 will be on the easier end of things. There will be a more challenging problem on the third exam in terms of related rates, because you actually do need quite a bit of time to kind of absorb that. I'm sure you'll spend all spring break doing related rate problems. Yeah, so we still need to do some implicit differentiation. We introduced the idea last time. Any issues or anything any questions I need to ask or answer? We're okay? All right. So let's try some more implicit differentiation. Looking through the homework problems here, I'm going to make up a problem that's kind of in line with what I think would be fair on a test. All right, so this is not related rates, just so you know. This is still implicit differentiation. So let's take a look at this equation here. Let's go square root of x squared plus y equals 5x minus x cubed y to the fifth. All right, so we have an equation, right? And we could graph this. I mean, we could ask the computer to graph this for us. And what we're trying to figure out is can we determine the slopes of the tangent lines at certain points on the curve? There's no easy way to solve for y or x here, so you cannot get this explicitly in terms of one of the variables. So you just have to take the derivative as is. So I need to be able to tell you first what derivative I want. Remember last class, I ended class telling you a little story. What's important is for whoever's asking for the derivative, for them to tell you what is your independent variable and then what would be your dependent variable. In this case, I would like to know, or I'd like for us to find, let's go with dy dx, which is our standard derivative, right? The notation for that, we also call that y prime, all right? So I'm going to start on the left side, and I'm going to take the derivative of what I see over here. And so I see that I have the square root of something, right? And so I have to start with a chain rule, which says take the derivative of the square root of something. And we know the derivative of the square root of something. This is that little line I'm letting you know I'm taking the derivative. Derivative of the square root of something is 1 over 2 square roots of that something, x squared plus y. That is the derivative of the square root of the, we call that the radicand. Okay, so the square root of that, the derivative is this. Then the chain rule says I multiply now by the derivative of what was in there, right? And what's in there is a sum. It's two things being added together, so I can do those separately, right? So I'm going to take the derivative of x squared, which is just going to be 2x. And that's because I'm differentiating with respect to x, and my independent variable here is x, right? So anytime I take the derivative of something that has x in it, it's going to be your standard derivative. So I have 2x there. Now I'm already kind of missing something. What should I have put? Parentheses, okay? And the reason is because it's multiplied times the derivative of this, and if that's two different terms, then I need that to distribute. All right, so that's fine. Now, plus, now the derivative of y. dy dx. Okay, this is dy dx. Now, do you prefer me to put dy dx, or do you want me to put y prime, or do you not care? You want dy dx? Okay, let's go dy dx. I forget on my homework solutions whether or not I use dy dx or y prime. I use y prime? Okay, so understand that this is the same thing, all right? Y prime.
Just like you said, it's less confusing this way compared to...
This notation is going to be a lot better in 2.7. We won't use this at all in 2.7. All right. I close the parentheses because I'm done, right? Left side's done? Okay, equals. Now, the derivative of 5x with respect to x is just 5. Because derivative of x is 1 and the constant comes along for the ride. Okay, minus, and now I take the derivative of this, but this is a product. So I must bring out the product rule for that, right? And we know the product rule is going to be, f prime g plus g prime f, all that stuff. And so I'm going to have multiple terms, aren't I, when I do the product rule? So I'm going to get my parentheses set up here so that this minus sign will distribute to whatever that derivative is. Okay, so let's start with this product rule. Derivative of x cubed times this, and then, yeah, okay, so it's what, 3x squared, just your standard derivative. And I multiply that times what? Y to the 5th power. Then I say plus, so this is my f prime g plus now g prime. So derivative of y to the 5th is 5y to the 4th dy dx. That is the critical piece right there, that dy dx. So remember, that was the chain rule part, right? That's, you're taking derivative of something to the 5th power, the 5 comes out, power goes to 4, but then you have to go and take derivative of what's in there. This time the derivative of y is not 1, it's dy dx. So it gets slapped onto the outside. Okay? I'm not done though. I need to finish off the product rule times x cubed. Okay, anyone have questions there? All right, that is our derivative. All right, this is it. This is the application of implicit differentiation on the equation. Now what we want to do is try and isolate dy dx. We want to get, see I have a dy dx there and a dy dx there. We need to get that, every term that has that in it on one side of the equation, everything that doesn't on the other. But I can't do anything until I free this thing from this parentheses, and I can't do anything to this till I free it from this parentheses, which means I must distribute here, and this minus sign must come through like this. All right, so let's talk about what this is going to look like. This times 2x, this just goes on top, right? And the 2's will cancel. So I should just get x over square root x squared plus y. And then when I go from here to here, I'm going to have the dy dx times this. So it really doesn't matter how you write this. I'm going to write it like this. I'm just going to slap the dy dx onto the back of this. You could have put it out front, but I'm just going to put it in the back. Equals a big dot, and then 5, and then let me just distribute the negative through. So minus 3x squared y to the 5th, and then what do we have here? Minus 5x cubed y to the 4th dy dx. So just be careful, it's not a 5 going through, right? The 5 is by itself. It's the negative going through. So I put those together, and then I did the x cubed. I went ahead and brought it out here next to the y to the 4th. So we good there? Okay, now I'm going to just look at the terms that have the dy dx in it. I have this term, and I have this entire nasty, ugly looking thing right there. So I need both of those on the same side of the equation, and it doesn't matter which side you go to, all right? So what would you do? Move everything to the left or to the right?
To the left.
I would go left also, because this is negative. If I bring it over, it's going to be positive, and I just would rather work with that. But you could bring that one over here. It's really your call at this point. All right, continuing. I'll leave that up there just so I have it if I need to refer back to it. All right, so we've got this piece here, which was the 1 over 2 root x squared plus y times dy dx. Then I brought this one over to the left side, which means it's now plus 5 x cubed y to the 4th dy dx. And then equals, now I had this term on the left side did not have dy dx in it, so I'm going to move that one over to this side. And it's going to join up with the 5 and the minus the 3x squared y to the 5th. That's already over here. So I have 5 minus 3x squared y to the 5th, and now I have minus this ugly fraction, like that. And the whole point of this was to be able to factor out a dy dx from both of these terms. So I'm going to pull that out. Now, to save myself a little bit of time, because I don't want to write this all out again, if I factor this out, this is what I'd have, right? The dy dx came out of both of those. So now that is in parentheses. And final step is to take this entire expression in parentheses and get used to this being ugly. It's going to look ugly, all right? Take this whole thing and you're going to just put a big division bar here and just slap it underneath this thing. And we're there. It's ugly, but it should be. It's a complicated curve. The derivative should be something pretty complicated. So it's 5 minus 3x squared y to the 5th minus x over root x squared plus y, the entire expression over 1 over 2 root x squared plus y plus 5x cubed y to the 4th. There you go.
Would that even be a curve, or would it be something in 3D?
Would what?
Would it be a curve or something in 3D?
No, it's a curve. It's still, this equation right here is a curve in 2D. All right. I don't think we're going to graph it. I was thinking maybe we graph it and just see what it looks like, but you know. Yeah. All right. So just remind me, what would somebody have to give me in order for me to actually find the equation, or the, well, I could find the equation of the tangent line too, but to find the slope of the tangent line, what would someone have to provide me? An x and a y. And that x and y can't just be any x and y, right? It has to satisfy this original equation, right? I wonder, could we come up with an x and a y that would work just for the sake of doing it? 0, 1? Is that what you said? Will 0, 1 work? I don't think 0, 1 will work, because then this side would be 1 and this side would be 0. 1, 1? Yeah, we would have to mess with that to try and get something, wouldn't we? I think 0, 0 works. Right? This is interesting, actually. 0, 0 works, doesn't it? 0, 0 lives on that curve. But what is the slope of the tangent line at 0, 0? So what would happen if I try and plug 0, 0 in here? What would I get on top? Ooh. That would be 0 here, wouldn't it? This would be like 0 over 0. It looks like the derivative is undefined there. Doesn't it look like that? Which means what? We probably have a cusp or a corner. Let's graph it. Let's just graph it. I was trying desperately to find, oh good, I'm already here. Okay, so let's try this. It's going to be square root of x squared plus y equals 5x minus x cubed times y to the, oops, that's not right, times y to the 5th. Oh yeah. Okay, so I don't know if y'all can see that here, but we've got a major mess here, because we have this point, right? But look at that. I mean, if you come in, the slope of the tangent line looks like looks like it's doing something like this, and then it almost looks like it's becoming infinite, doesn't it? But there's a bigger problem, is that if you come in from the left-hand side, your slope of your tangent line is something completely different. That's why this is actually a disaster. And it matches up with what's happening here, right? Like we have a disaster happening in terms of tangent lines at 0, 0. Now, I don't think I can just look at this and see a point that would be, is this a point? Is 2, 1 on our graph? Is 2, 1 on our graph? Let's see. Is 2, 1 there? If I plug in 2 for x and 1 for y, let's see, what will we get here? Root 5? No, I don't think that's going to work. No. Yeah, that's not going to work. Okay, so that looked like it was the point 2, 1, but it's not. It's something else. So I don't think I'm going to be able to find a point easily. Do y'all understand that? Okay. But if I could, now, how would I find a point? If I had to, if someone forced me to find a point other than 0, 0, what I could do is I could just pick a value for x. Like let's pick a value for x2, and let's go find y. So we'd rewrite this as square root 4 plus y, because I'm squaring 2, equals 10 minus, now 2 is going in there, so 8 y to the 5th. Now you have to solve that equation for y. And that equation would not be easy to solve. How would we solve that? Well, there's a way we can solve this, but it's not till later on in this class. And it's using what's called Newton's method. And it's actually the way computers solve equations. And so we could get a computer to solve this, but we could also use a method by hand to do it. It's not easy, though. So like when you're in college algebra, you only solve equations up to a certain level of difficulty. And then when you get to a certain level like this, there's no like nice, clean way of doing it. So we rely on algorithms to do it and use computers to do it. But the computer algorithm relies on calculus, which I'll show you later. Okay? All right. We're done with this. Let's do another example. Oh, where's my book? There we go.
You didn't do anything. It's all you.
Let's look at x to the 4th plus y to the 4th equals 16. I would like for us to find y double prime. In other words, I want you to find the derivative of y with respect to x like that. Remember on the Leibniz notation, when we wanted the second derivative, we had to offset the 2's so that people didn't think it meant square the derivative? Okay, so that means the second derivative. But I am asking you to treat x as your independent variable again. Okay? All right, so what we're going to do is we're going to take derivative, and then we're going to take derivative again. First derivative, when I take it with respect to x, 4x cubed plus 4y cubed dy dx equals 0. Do y'all agree with that? Which is the same as x cubed plus y cubed dy dx equals 0. What did I do there? I just divided by 4. I noticed that I had a 0 on the right-hand side, and I have 4 in both of these terms. And just to make things look a little nicer, I just divided everything by 4 and killed it off. That's a legal move, okay? Now watch this. I'm not going to solve for dy dx. I'm going to do the derivative again. Because this would be a second application of the derivative, wouldn't it? Okay, so what is the derivative of x cubed? 3x squared. Now, this is where things get a little messy. Plus, I have to take derivative of this, right? This is a product, right? I must apply a product rule to that. So carefully, let's go through this. What is the derivative of y cubed? 3y squared times dy dx. That is the derivative of y cubed, isn't it? Times this one, which is just dy dx again. See, it's this is the first derivative, isn't it?
Yes.
And then you're doing times the first derivative again, times the first derivative again. That means it's the first derivative squared, right? Plus, I'm still doing product rule now, the derivative of this, which is the second derivative. See, that's where your second derivative is going to come from. Understand what I just did or no? No? Okay, let me go back through this again. I'm doing product rule on this. This is my f, this is my g, right? So this right here is f prime. If I ask you take derivative of y cubed, right? With respect to x, you're going to say 3y squared dy dx. Okay, so that's your f prime. Now, the next part of the product rule says multiply it times g. Multiply it times g. Well, what was g? G was dy dx. All right? So I'm multiplying these two together. So if you really want to look at this, these two together, when I put them together, this is actually dy dx squared. Not the second derivative. It's the first derivative squared. That's what this is. But then when I come to do what, g prime next? G is the first derivative. So I'm taking the derivative of the first derivative, which is your second derivative. So g prime right here is going to be d2y over dx2, like that, second derivative. Understand? So that's g prime, and then times, finally, this will be f, which is y cubed. So I have now done this, right? I've done the product rule, equals the derivative of 0, which is still 0. All right, so let me rewrite this. I have 3x squared plus 3y squared, the derivative of y with respect to x squared, plus the second derivative of my function times y cubed equals 0. Do you see now why this notation is so important, that you have the two offset and so you don't confuse it with this? These are totally different things here. All right, now I'm trying to find this, right? So let me isolate it. Let me get it by itself on one side of the equation. So let's get this by itself. So let's move everything else to the other side. And I'm going to leave the first derivative here, okay? But I'm gonna move it up here, so I'm gonna erase these 4s here. That was my first derivative, right? That's my first one. Let me just, so we don't confuse ourselves. So now I have this. I have the second derivative equals negative 3x squared minus 3y squared, derivative of y with respect to x squared, all over y cubed. Okay, so what did I do here? I moved these two things over, right, which made them both negative. And then I had this by itself, and I didn't want the y cubed there, so I divided y cubed on both sides. So that's our second derivative, right? You sure? No questions? So if you wanted to know what the second derivative of this function was, what would someone have to give you right now? They would have to give you the first derivative. They would have to give you a point, right, on the curve. And they would have to give you that x and y coordinate. And then they would have to go figure out what the first derivative was at that x and y. So I'm going to continue. I'm not done. This is a pretty good answer. But I'm going to go replace dy dx with what it is. So I'm going to go back up to this, and I'm going to solve that for dy dx. All right? So let's go back to that first derivative and solve it for dy dx. So solving this one for dy dx, I get, whoa. Yeah. dy dx is, what's it going to turn out to be? Negative, right, x cubed over y cubed. So you just move the x cubed over, it becomes negative, divide by y cubed, you get negative x cubed over y cubed. So now let's go back to this. This, jump over the dot, come right here, negative 3x squared minus 3y squared times the derivative of y with respect to x, which was this, negative x cubed over y cubed, but all of that squared over y cubed. So there's my first derivative, right? Right there. Squared. Now let's actually square that. Negative 3x squared minus 3y squared. Now when I square this, the negative won't matter anymore, will it? And what happens when you take x cubed and you square it? X to the 6th over y to the 6th again, all over y to the 3rd. I'm almost there. I can start cleaning up still. Do y'all see what I can do here? Those y's, do you see these y's here? Since that's multiplication, I can just kill off 2 factors and make that a 4, can't I? Y'all have questions? Negative 3x squared minus 3 what? X to the 6th over y to the 4th, and then all this over y to the 3rd.
Can we put each term under, above y to the 3rd?
Oh, like put that over this and this over this? Yeah, you could split it up. At this point, I mean, if somebody hands me x and y, I'm good to go, right? If somebody gives me an x and a y, a point that lived on the original graph, then I would be set, right? I'd be able to get the second derivative. Now, how you clean this up is kind of, there are different ways if you wanted to take this even further. Like here's something I could do. See if you follow me here. This equals negative 3x squared y to the 4th minus 3x to the 6th over y to the 7th. So what did I do here? It's kind of like a common denominator. I wanted to clear this y to the 4th out. I didn't want a fraction here anymore. So what I did is I decided to multiply y to the 4th over y to the 4th on the top and bottom of this equation. When I distribute this to this, I get that, right? When I distribute this to this, the y to the 4ths cancel, and I just get this. And when I do this to this, I get that. And that's a pretty clean looking answer right here, isn't it? You could even go and split this up into 2 now, but if I split it into 2, one of them is going to be a fraction again. But, you know, or both, actually both, because the denominator's got a higher power. But either way, I mean, we're pretty clean, right? That's pretty clean? Okay. All right. That's it. Now, let's try and remember what the heck this is all about. Like, we start to lose sight of what the derivative is once we start getting into implicit. So I want to try and graphically help you understand what's going on here. The idea is this. If we have a graph, here's x, here's y, and we have some sort of curve, all right? So this is some implicit equation, all right? So there's some graph. I didn't mean for it to look like a figure 8, kind of like that. But that's some curve, right? So if we pick a point on this graph, let's say we pick that point right there, xy, then dy dx means what? Well, it means that if x changes a little bit, well, let me say it a different way. This tells us the instantaneous or instant rate of change in y as x changes. Okay, so what happens, what this dy dx means is that if x changes a little bit, so if I start to try and move that direction, it tells me how fast my y has to change. And that basically gives me a slope, right? It's almost like if we zoomed in on that little piece, that little infinitesimal piece, right? That's my zoom in. Can you all see my zoom in there? And here's the curve coming through, and here's that point. What it's doing is it's saying, all right, take a little change in x, and then this is your change in y. And this divided by this is your rise over run, that's your slope, okay? And that gives you basically that slope of that line right there. Understand? But these are like very, very tiny infinitesimal changes. Yes? The difference between that and dx dy is that it's the same picture, okay, but let me draw it this way. It's the same picture, but this time what's changing? Y is changing, right? Y changes a little bit, so what happens is y changes a little bit, and I'm trying to figure out how much x changes by. Now, they are not necessarily the same answers. I know that that seems strange, but they're not, because it's the flip of the slope. It's the reciprocal of the slope. So this would mean right here, the instant rate of change in y, I'm just going to say that this becomes x and this becomes y, right? If we do it this way. Y'all with me? Okay, what's important about that is what I'm about to do. I think the next thing I put up here is pretty mind-blowing, all right? If you really take a step back and look at what this means, all right? And this is going to lead us into related rates. Okay, I'm going to take an equation, the first equation I could think of that pops into my head here from chemistry. The first one I could just think of. You may or may not have seen this before. Had what?
How to integrate that in one of his classes.
This equation? Yeah. Now I may not have used the appropriate lower. That might not be the right R. It might be lowercase r, but is it lowercase r?
No, it's a lowercase n. Your
Is it? All my n's are always look uppercase. Okay. Ideal gas law. Okay, so if you've never seen this, this is an equation. It's been proven to be true, and each of these letters means something. So P stands for pressure. All right. V stands for volume. N is something, R is something, T is something. T is temperature. Okay, temperature. All right. What is N? Anyone know what N is? It's moles, number of moles. If you, this is not a chemistry quiz, okay? Number of moles, and then what is R?
0.0.
It's a constant, right? Is it Avogadro's number? No. It's not Avogadro's. It's what? Yeah, I don't care what it is, though. It's a constant. It's a constant. All right. So look, when you look at this equation, you can really take these two and think both of those are basically constants. Okay, these two are constant. Oh, and I need to kind of explain what's going on here. You have a container. all right? You have some sort of vessel, let's say it's a cylinder. You have some container, right? This container has a volume to it. That's how much material it can hold, all right? You have some substance in here, and there's going to be, you close it off, right? You completely shut it, you know, put the lid on it, whatever, tighten it down, and then you have a volume, right? You have your volume, you have a certain pressure within the container, and then you have a certain temperature within the container, right? And then the number of moles is related to how much stuff you have in there. Like, you know, say you have some liquid in here. Number of moles is going to be fixed, and then this is a constant. It's not Avogadro's number. What is it?
It's like a constant.
2.12.
Yeah, but it's called something though.
It's a constant dependent on the element, I thought.
Well, who cares? It's a constant. All right. Anyway, okay, so the thing that's super cool about this equation is that it kind of makes sense if you think about, if you've ever had, yes?
Ideal gas constant.
It's just called the ideal gas constant? Okay, whatever, all right. I don't know why I wanted to say Avogadro's number.
0.8206.
So look at these two as being a constant, all right? So, I mean, it may as well be the number 10. It's not, but let's just say it's like the number 10 here, all right? What happens here is that you have to maintain equality, right? So if your temperature goes up, what has to happen here? If this side of the equation gets bigger, then this side has to get bigger, right? So either your pressure has to go up or your volume has to go up, right? And if we're going to assume that this container, we can't just like change its shape and make it bigger, right? Then if temperature goes up, pressure has to go up. If temperature goes down, pressure goes down. So like if you've ever had like a soda or something, maybe sitting at room temperature, and you open it and it goes, you know, you hear the gas escape. I don't know if you've ever noticed this, but the gas that's escaping is normally cooler than the actual ambient temperature. So as the gas comes out, it's colder than the air around it. Does that make sense? Have y'all ever noticed that?
Yep.
Okay, that's this law. If I open the container all of a sudden, what happens? Pressure drops, right? I've released the pressure. This side drops. And to maintain equality, this side has to come down. And the only thing that can change if these two are constant is temperature has to come down. All right, another place this is used is air conditioners. All right, y'all know how an air conditioner works? If you don't, I'll explain it as easy as I can. What you have, and look, I'm not going to get too technical here. I'm going to make this very, very basic. You have a liquid here. All right, this is Freon. Then what happens is it's pumped out and it gets compressed. Compress this. So you take that liquid, you compress it. Is that right?
Yes.
And then you have this little orifice, this little tiny hole, like a pinhole. And what happens is at this pinhole, I'm going to mark that pinhole with a line, okay? What happens is it sprays out of that pinhole. Okay, so on this side of this line, you have this under high pressure. And then when it sprays out through here, it goes into a larger chamber, and it's under low pressure here. So the pressure changes here to here from high pressure to low pressure. So you have very high pressure, then all of a sudden in an instant, it drops to low pressure, and to maintain the ideal gas law, that means the temperature has to drop. So the gas, as it comes out on this side as a gas, it's going to come out very cold, okay? Because the temperature dropped. So this is very cold. Now you've got a very cold gas in here, and what you do is you take a fan and you blow just regular air over this very cold pipe. And this pipe will run back and forth like this with the cold gas in it and the coils, right? And then you're blowing a fan over these cold coils. That air basically absorbs the heat, right? I mean, these coils absorb the heat, and so the air coming out the other side is going to be cold. All right? Now this comes through, and eventually what happens is that this goes back to a liquid and comes back into the container, and then it just recycles and just keeps doing that over and over and over.
What goes in compressor?
well, yeah, it goes through compresses and all that, whatever. But that's basically the loop. But it depends on this ideal gas law, okay? So this is not free. This costs, there's a lot of energy that has to be used to do this because you have to compress it, right? It's not free cold air. You have to compress it, and that's where the major cost of an air conditioner is. It's the electricity required to run the compressor to pump it. And then you have to run the fan, right? So the cost, that's why it's, in the middle of the summer, it's very expensive because this is always running. All right, ideal gas law. Now, what does this have to do with implicit differentiation? Everything I've done up to this point, in terms of differentiation in this class, we've always had an equation that has just x and y in it, right? We've had just x and y. We've never dealt with an equation that has more than two variables. And in this equation, you could argue that this has three variables. The n and the r are constants. So I'm curious, if the temperature changes just a little bit, how does the pressure change? So instantaneously, if my temperature changes at an instant, it moves, the temperature moves just a little bit, how is the pressure affected by that? How does the pressure change? But instantaneously, right? Or I could say, look, if the temperature changes, how does the volume change? Or if the volume changes, how does the pressure change? I can look at this from many different perspectives and ask all of the following questions. I could ask, what's dP dt? What is the instantaneous rate of change in pressure with respect to temperature? So if temperature changes a little bit, how much will pressure change? Understand? I could ask, what's another one I could ask? dP dV. If volume changes a little bit, how much will the pressure change? What else could I ask? dt dV. I could go dt dP. I could do dV over dt. I could do dV over dP. There are 6 different derivatives that I could be looking at here. Right? 6 of them based off this one simple equation. So let's just go after one of them first, okay? Let's go after this one right here. Let's find dP. And this, remember I said this is mind-blowing? The thing that's mind-blowing about this is this works for any equation. Out of chemistry, physics, biology, doesn't matter where you grab your equation from, you can always talk about how one variable is related to another variable in terms of instantaneous rates of change by just differentiation. And specifically implicit differentiation because you have all these different variables. Okay, you ready? So what I'm going to do is I'm going to differentiate this. I'm going to differentiate that with respect to capital T, right? Which means capital T is my independent variable. Everything else depends on capital T. All right, so let's try to take the derivative of the left-hand side. What do you see happening on the left-hand side? A product. This is a product, isn't it? So we have to do a product rule. So the derivative of the left side will be, what's the derivative of P with respect to T? dP dt. dP dt, right? Times, so we're doing f prime g plus g prime f, right? So f prime we've got, now times g, which is really v, plus, okay, now the derivative of v with respect to t, dv dt. That's supposed to be capital T. dv dt. See, the independent variable here is capital T. So if I take the derivative of v, it's not just 1 or anything like that because We are saying the volume depends on temperature. So the rate at which the volume changes with respect to temperature is not 1. We're going to get a 1 here eventually, but not yet. F prime G plus G prime F. So what goes here? Times P. Any questions on the left side product rule? Okay, equals. Okay, N times R is a constant. So it's just going to come for the ride. NR. And now, what is the derivative of T with respect to T? 1. Right? There's where you get the 1. Understand? It's not a product rule here because that's a constant. So it's like if I take derivative of 5x, you don't do a product rule here. You just bring the 5 along and take derivative of x, right? That's what I'm doing there. I'm bringing the NR along, and then I'm just taking derivative of t with respect to t, which gives me the 1. This good? Now what are we solving for? We're trying to figure out dp dt, so I need to isolate this. So I'm going to move this to the other side. So dp dt times v equals nr minus dv dt times p. So I move this piece to the right side, get that. And finally, divide by v. Kill that off over there. And that's it. We're done. We now have a formula that gives us the instantaneous rate and change in pressure with respect to temperature. I can tell you how fast the pressure is changing with respect to temperature, but what do you have to give me in order for me to do that?
Pressure and
I need pressure, I need volume, and I need, this is the key. I can't make this any better for us. This is, you're going to have to be able to give me this. You're going to have to be able to tell me how fast the volume is changing. Right? You're going to tell me, okay, at this instant in time, what's the volume? At this instant in time, what's the pressure? And at this instant in time, how fast is the volume changing? If you can tell me that, I can tell you how fast the pressure is changing. So this is, you're going to see in the next section that in all the problems we do, we're going to have situations where we're going to be given these derivatives are going to be part of the given information. And that's so we can calculate other derivatives, if that makes sense. All right, should we do another one of these? You want to try to get out, there's 6 different ones that we could do. How about you try one on your own? How about, I don't know, do this one right here. Do that one right there. Go dv dt, see if you can get that. Okay, so that was the answer for that one. If you get that one, I have the answer on the board. If you get that one, try, you know what? No, don't try that one. Try this one. That one's going to be a little bit different. If you have a question, raise your hand. I'll come by. So that's 1. So you just brought it over, divide by v. Yeah, that's it.
Okay.
Yep. Wait, on the right side, let me see that right side for a second. Yeah, you have that dt, dv. Yeah. Yep.
Why is it dp over dv?
Okay, so v is our independent variable, right? So we're differentiating everything with respect to v. So you still have to do product rule, right? So let me get to this side. That's a constant, comes down. What is the derivative of t? Oh, where? Right here? Where's, oh, did I write that down wrong? Hold
Yeah, I
on.
thought it was.
dv. This is capital T, first of all. I keep on doing lowercase t. Okay, dp dt v, and then dv dt p, and then this is 1. And then did I just not bring it over right?
You put NR minus DP dV.
dp.
That's supposed to be a t.
dp over dt. dt.
Yes.
Oh, there you go. Yes. Yes, you're not crazy. Sorry about that. I messed up that v. Where did I get my v from? It's right here. It says t here. So I moved that one over, then divided by p. I'll give you another maybe minute. See if anyone else has any more questions. I didn't solve the second one yet for dp dv. I just want to make sure everyone understood the derivative first.
How would this be solved?
Yep, you bring the, hold on. You're trying to solve that one. So you, yeah, because that's a 1, so it's going to be p comes over first, divide by v. Yep. Yep. So this is going to be a 1. Okay, what do you think? Questions? The second one, the big difference is, you know, on the right, the previous two I gave you, it was the right side that turned into a 1 because you did dt dt, and that's 1. But on this on the last one I gave you, you're differentiating with respect to v. So when you do your product rule, the dv dv is the one that turns into 1. And this side, the dt dv does not turn into 1. Okay. All right, well, you should be able to get through your homework for 2.6. And now I think we need to officially start 2.7, which is related rates. And before I put anything up here, because I have all sorts of animations and stuff to show you, let's kind of stick to the same theme that we just had on the board. I'm going to give you a different formula now. Different, you know, we just use the ideal gas law. Let's do something more more mathy. How about this formula? Area is pi r squared. I mean, that's an equation, right? We've known that for a long time. That's the area of a circle, isn't it? So if I have a circle of radius r, that formula will give me the area of that circle. Yes? So if r is 2, then what's a?
Pi 4.
4 pi? What if r is 3? What's a? 9 pi. What if r is 4? What's a? Okay, what if r is 5? All right, this is, I'm just basically quizzing you on your perfect squares here, right? What if r is 1? Pi. And of course, if r was 0, what would your area be? 0, right? So in a pre-calculus class or geometry, if somebody gives you a fixed radius, you can find the area. And that's not, there's no calculus involved in that at all, right? I'm curious though, if calculus is more about rates of change, let's talk about what's happening as our radius is changing here. How much does our area grow by when we make that first step from 0 to 1? How much does my area increase by? It increases by 1 pi, right? How about on the second step? My radius goes up by 1, but my area goes up by how much? 3 this time. And then my radius goes up by 1 again, and my radius this time goes up by 5 pi, all right? And then radius goes up by 1, but this time it goes up by 7 pi. And next time, 9 pi. And there's kind of a pattern to this, right? Looks like it's going up by odds. Yeah? So if I go out, what I want you to see is this. If I'm sitting at a radius, let's say I'm sitting at a radius of 1, and I increase my radius to 2, the area is going to jump up, right? That would be, if I'm sitting at 1, and I change it to 2, my radius goes up by 3. But what if I'm sitting at a radius of 20, and I jump it up to 21? My radius is not going to go up by 3 pi, right? It's going to go up by a lot more. So just visualize this. You have a small circle. You increase the radius by 1. How much area did you add to that? So let's say this is radius 1. You increase the radius by 1. What you've done is you've added that much more area, right? But if you were to take a circle that had a huge radius to start with, and then you increased it by 1, you're adding all of this, aren't you? All of that. And that's a whole lot more area than that was, right? So as the radius gets bigger, the area is increasing faster. That makes sense? The area increases faster as the radius gets bigger. So one question we could ask ourselves is, if, let's say we start with a circle,